Welcome to this problem-solving session. Today, we'll explore problem number 1017, titled Convert to base -2. This unique problem challenges us to think outside the box by working with negative bases in number systems. Let's dive in and break it down step by step. The problem asks us to convert a given integer n into its representation in base-2. Unlike standard positive bases, base-2 is a negative base, which means the powers of -2 alternate in sign. The digits used in this base are still 0 and 1, but the way numbers are represented is different. For example, the number 3 in base-2 is written as 111 because when expanded, it equals 3 equals -2, (2 plus, -2, (1 plus, -2, (0). Similarly, the number 4 is represented as 100 because it equals 4 equals -2, (2). The task is to compute this representation for the input integer n and return it as a string. The input value n will always be between 0 and 10 to the power of 9, inclusive, and our output must strictly follow this base-2 representation format. To understand this better, let's look at some examples. If n is 2, the output should be 110. Here's why: the number 2 can be expressed as the sum of powers of -2 using -2, (2 plus, -2, (0). This means the coefficients for these powers are 1, 1, and 0, respectively, which gives us the base-2 representation 110. Another example is n equals 3. In this case, the output is 111 because 3 can be broken down as -2, (2 plus, -2, (1 plus, -2, (0). The coefficients here are 1, 1, and 1, leading to the representation 111. Now consider the case where n equals 4. The output for this input is 100. This is because 4 can be expressed as -2, (2 alone, with no contributions from smaller powers of -2. The coefficients in this case are 1, 4, -2, (2, and 0 for all lower powers, resulting in the base-2 representation 100. These examples highlight the process of decomposing the number into powers of -2 and determining the coefficients, which form the digits of the output string. The constraints ensure that the input n will always be within the range of 0 to 10 to the power of 9, so our solution must handle this range efficiently. There are a few important points to keep in mind for this problem. First, the output must always be a valid base-2 string representation. This means it should not have any leading zeros, except in the special case where n is 0. In that case, the output must be exactly 0. Additionally, for numbers that are exact powers of -2, such as 4 or 16, the output will be a string starting with a single 1 followed by zeros, like 100, 0. Finally, the largest value of n, which is 10 to the power of 9, must be handled efficiently by our solution to meet the constraints. These notes emphasize the importance of correctness and efficiency in our approach to solving the problem. To approach this problem, the most straightforward method we could consider is a brute force approach. The idea here is to repeatedly divide the number n by -2, keeping track of the remainders at each step. This process is similar to converting numbers to other bases, like base-2 or base-10, but with the added twist of handling a negative base. One key insight is that, for base-2, the remainders we care about are still just 0 or 1. However, since the divisor is negative, we might occasionally get a negative remainder, like -1. In such cases, we adjust the remainder by adding 2 and incrementing the quotient by 1 to ensure the result remains valid. While this method is intuitive and easy to understand, it requires careful handling of these adjustments, which can be tricky at first. On the plus side, the approach is computationally efficient because each division step reduces n logarithmically, making the algorithm run in O log n time. An optimized version of the brute force approach streamlines these calculations by directly incorporating the adjustments for negative remainders into the process. Here's how it works. First, compute the remainder of n when divided by -2. If the remainder comes out negative, we correct it by adding 2 and incrementing the quotient simultaneously. After that, we update n to be the new quotient and repeat these steps until n becomes 0. What makes this method efficient is that it eliminates any unnecessary recalculations, ensuring correctness in fewer steps. The representation is built systematically, starting from the least significant digit and working up to the most significant digit. Like the brute force method, this approach runs in O log n time since we divide n by -2 at each iteration. Alternatively, a recursive approach could be used to achieve the same result. Here, instead of using a loop, recursion is employed to handle each digit. The base case occurs when n equals 0, at which point the recursion unwinds and combines the results. While this method is elegant and concise, it has a potential drawback. For very large inputs, the depth of recursion could lead to a stack overflow, making it less robust than the iterative alternative. Among the three approaches, the iterative optimized method stands out as our chosen strategy. We selected it because it balances simplicity, efficiency, and robustness. Unlike the brute force approach, this optimized method avoids redundant operations and handles negative remainders in a more controlled, elegant way. At the same time, it sidesteps the pitfalls of recursion, such as stack overflow, and is easier to debug when issues arise. One of the most surprising and fascinating aspects of this problem is the fact that a negative base, like -2, can still represent numbers using only the digits 0 and 1. While this might seem counterintuitive, it works due to how the remainder adjustments are handled during division. Additionally, the iterative approach builds the representation from the least significant digit to the most significant digit, a pattern that is consistent with how base conversions generally work. This clarity and predictability make the iterative method a natural choice for solving this problem. When comparing the approaches, the iterative method emerges as the most practical solution. It is more space efficient than the recursive method because it avoids the overhead of maintaining a call stack. This makes it better suited for handling larger inputs. Additionally, compared to the brute force method, the optimized approach is cleaner and more robust, reducing the number of edge cases that need to be managed explicitly. In summary, the iterative optimized approach strikes the perfect balance between simplicity, speed, and reliability. It runs in O log n time, directly constructs the solution without unnecessary complexity, and avoids potential pitfalls like stack overflows or convoluted adjustments. For these reasons, it represents the most effective and elegant strategy for solving this problem. To solve the problem of converting a number into its base -2 representation, we can follow a systematic process. We start by initializing a few variables. The input number n is our starting point, and we create an empty list called result to store the digits of the base -2 representation, but in reverse order. This list will be built as we compute the individual digits of the number. The algorithm works iteratively, so we set up a loop that continues until n becomes 0. The loop will handle the core operations of the conversion process, ensuring that we calculate each digit correctly for the negative base. The next step inside the loop is to compute the remainder of n when divided by -2. This is crucial because the remainder determines the current least significant digit in the base -2 system. If the remainder is negative, which can happen due to the negative divisor, we adjust it by adding 2 to make it non-negative. This adjustment ensures that all digits in the result are valid for base -2, which only allows 0 or 1. After adjusting the remainder, we append it to the result list. Finally, we update n to the quotient of the division. If there was an adjustment to the remainder, we increment the quotient by 1 to maintain consistency. This iterative process ensures that the digits appended to the result list are accurate for base -2 representation. Once the loop has processed all digits, it will terminate when n becomes 0. At this point, we will have computed all the digits of the base -2 representation, but they are stored in reverse order in the result list. This happens because the iterative process computes the least significant digit first and progresses toward the most significant digit. To obtain the correct order, we reverse the result list. This gives us the final sequence of digits representing the number in base -2. Optionally, we can convert the reversed list into a single string for easier readability, though this depends on the output format required. Alternatively, if the problem only requires the list of digits, we can return it directly. A key insight here is the unique nature of negative base conversion. Unlike standard base conversions, where the divisor is positive, the negative divisor introduces additional complexity. Specifically, the remainder from the division can be negative, which is not valid in base -2. To address this, we add the base, in this case 2, to ensure the remainder is non-negative. This adjustment, however, impacts the quotient, which must then be incremented to preserve the mathematical relationship between the quotient, remainder, and divisor. These steps ensure that the algorithm produces a valid base -2 representation. The reversal step is a fundamental aspect of converting any number into a different base. Since the calculation proceeds from the least significant to the most significant digit, reversing the order at the end ensures the representation is correct. Additionally, the algorithm is designed to handle edge cases gracefully. For instance, when n is 0, the algorithm directly outputs 0, since 0 in any base is still 0. For negative values of n, the properties of the modulo operation with a negative divisor ensure accurate calculations, as long as the remainder is adjusted appropriately. The data structures used in this algorithm are simple yet effective. The result list dynamically stores the digits as they are computed, allowing for efficient appending and reversal. Integer variables like n, remainder, and quotient are used to perform the necessary calculations. The operations involved are straightforward: modulo and division for computing remainders and quotients, adjustment of the remainder to ensure valid digits, and reversal of the list to produce the correct order. These operations, while simple, work together seamlessly to handle the unique challenges of base -2 conversion. Now, let's look at the pseudocode implementation. The function begins with a check for the edge case where n is 0. In this case, it simply returns 0. For other numbers, we initialize an empty list called result. The core of the algorithm is a while loop that runs as long as n is not 0. Inside the loop, we calculate the remainder of n divided by -2 and then update n to the quotient of this division. If the remainder is negative, we adjust it by adding 2 to make it non-negative. Since the adjustment changes the remainder, the quotient is incremented by 1 to maintain consistency. After adjusting the remainder, we append it to the result list. This process continues iteratively until n becomes 0. Once all digits have been computed, we reverse the result list to obtain the correct order of the digits. Finally, the function returns the reversed list as the base -2 representation of the input number. To analyze the complexity of this algorithm, we consider both time and space. The time complexity is O log n, where n is the absolute value of the input number. This is because, in each iteration of the loop, the magnitude of n approximately halves due to the division by -2. As a result, the number of iterations is proportional to the logarithm of the absolute value of n. For space complexity, the result list stores the digits of the base -2 representation. The number of digits required is proportional to O log n, as each iteration appends one digit to the list. Thus, the space complexity is also O log n. These complexities make the algorithm efficient for converting numbers to base -2, even for large inputs. The given code solves the problem of converting an integer n to its representation in base -2. The function baseneg2 is designed to handle both positive and negative values of n and follows a step-by-step process to compute the representation. First, the function checks if n is equal to 0. If so, it directly returns 0 as the base -2 representation of 0 is simply 0. This is an essential edge case to handle. Next, the function initializes an empty list called result to store the digits of the base -2 representation in reverse order. This list will be used to construct the final answer. The function then enters a while loop that continues until n becomes 0. Inside the loop, the remainder of n divided by -2 is calculated using n%-2. Simultaneously, n is updated to the integer division result of n///-2. These two operations are essential for the base conversion process. Since the modulus operation can yield negative remainders when working with negative bases, a correction is performed. If the remainder is negative, it is adjusted by adding 2, and n is incremented by 1. This ensures that the remainder always falls within the range 0, 1, which corresponds to valid digits in base -2. The adjusted remainder is then converted to a string and appended to the result list. This process continues until n becomes 0, at which point the result list contains the digits of the base -2 representation in reverse order. Finally, the list result is reversed and joined into a single string using .join, result, ::-1, which constructs the correct base -2 representation. The function then returns this string as the output. This implementation is efficient and handles all edge cases, including 0 and negative numbers, making it well suited for the problem requirements. This is the Java implementation of the convert to base -2 problem, following the same logic as the provided Python solution. The key difference lies in the use of Java-specific syntax, such as the string builder class for constructing the result in reverse order and explicit type declarations for variables. The implementation handles the conversion by repeatedly dividing the number by -2, adjusting for negative remainders, and appending the result to the string builder. Finally, the result is reversed to provide the correct base -2 representation. To convert the number 2 to base -2, we start with the initial input n equals 2 and an empty list for the result. First, we compute the remainder by taking 2%-2, which equals 0. Since the remainder is non-negative, no adjustment is necessary. Next, we divide 2 by -2, resulting in n equals -1. We then append the remainder, 0, to the result list, giving us result equals 0. On the second iteration, we compute the remainder of -1%-2, which equals -1. Since this remainder is negative, we adjust it by adding 2, making the remainder 1. Simultaneously, we increment n by 1, resulting in n equals 0. We then append the adjusted remainder, 1, to the result list, updating it to result equals 0, 1. With n now equal to 0, we stop the process. Finally, we reverse the result list and join its elements to form the base -2 representation, which is 10. This completes the conversion, and the output is 10. Now, let's convert the number 3 to base -2. We begin with n equals 3 and an empty result list. The first step is to compute the remainder of 3%-2, which equals -1. Since the remainder is negative, we adjust it by adding 2, making it 1, and increment n by 1, resulting in n equals 2. We then append this adjusted remainder, 1, to the result list, so result equals 1. Next, we compute the remainder of 2%-2, which equals 0. This remainder does not need adjustment. Dividing 2 by -2 gives n equals -1. We append the remainder, 0, to the result list, updating it to result equals 1, 0. On the third iteration, we calculate the remainder of -1%-2, which is -1. Adjusting this by adding 2 gives a remainder of 1, and incrementing n by 1 results in n equals 0. We append this remainder, 1, to the result list, giving us result equals 1, 0, 1. With n now 0, the process ends. Reversing the result list and joining its elements produces the base -2 representation 101. The output is 101. Finally, let's work through converting the number 4 to base -2. Starting with n equals 4 and an empty result list, the first step is to calculate the remainder of 4%-2, which equals 0. Since the remainder is non-negative, no adjustment is needed. Dividing 4 by -2 results in n equals -2. We append the remainder, 0, to the result list, making result equals 0. On the second iteration, we compute the remainder of -2%-2, which also equals 0. Again, no adjustment is required. Dividing -2 by -2 gives n equals 1. We append the remainder, 0, to the result list, updating it to result equals 0, 0. On the third and final iteration, we calculate the remainder of 1%-2, which equals -1. Since this remainder is negative, we adjust it by adding 2 to make it 1 and increment n by 1, resulting in n equals 0. We append this adjusted remainder, 1, to the result list, making result equals 0, 0, 1. With n now 0, the process is complete. Reversing the result list and joining its elements gives the base -2 representation 100. The output is 100. To analyze the time complexity of the algorithm, we start by looking at the number of iterations in the while loop. Each iteration reduces the magnitude of n by half, regardless of whether n is positive or negative, due to the operation n equals n//-2. This means that the number of iterations required to reduce n to 0 is proportional to the number of digits in its base -2 representation. Since the number of digits in any binary-like numeral system grows logarithmically with the value of the number of iterations is O log_2, n. Within each iteration, the algorithm performs a fixed set of operations, a modulo operation, an integer division, and adjustments for negative remainders, all of which are O(1). Additionally, appending a digit to the result list is also an O(1) operation. Therefore, the time complexity per iteration is constant, and the overall time complexity is determined by the O log_2, n, iterations multiplied by these O(1) operations. Combining these observations, the total time complexity of the algorithm is O log_2, n, as the logarithmic number of iterations dominates the computation. Now, turning to space complexity, the memory usage primarily depends on the storage required for the result list and any auxiliary variables. The result list stores the digits of the base -2 representation, and since the number of digits is proportional to O log_2, n, the memory required for this list is also O log_2, n. When constructing the final output string by reversing and joining the list, additional memory of O log_2, n, is needed for the string. For auxiliary variables like n, remainder, and the loop counter, the memory usage is constant, or O(1). Thus, the space complexity is dominated by the storage for the result list and the final string, making the overall space complexity O log_2, n. In conclusion, the space complexity of the algorithm is O log_2, n, driven primarily by the storage requirements for the result list and the final string. Comparing this to a naive approach, where base -2 representation might be calculated by iterating through powers of -2 and subtracting their weighted values, we see a significant performance difference. The naive approach would involve a time complexity of O, n, as it requires iterating through all relevant powers of -2 up to the largest one needed. This is far less efficient than the optimized algorithm, which achieves a logarithmic time complexity by relying on direct modulo and division operations. Additionally, the optimized algorithm minimizes space usage by avoiding intermediate calculations and directly constructing the base -2 representation. The time complexity of the algorithm holds consistently across best, worst, and average cases. In the best case, when n is very small, such as 0 or 1, the number of iterations is minimal. However, since the complexity is O log_2, n, the constant factors are small, but the asymptotic complexity remains the same. In the worst case, for very large values of n, the number of iterations is maximized, but even then, the logarithmic growth ensures efficiency. On average, for random values of n, the number of iterations still depends logarithmically on the magnitude of n, keeping the time complexity at O log_2, n. This logarithmic behavior is mathematically justified because, in any positional numeral system, the number of digits required to represent a number grows logarithmically with its value. This iterative halving of n in base -2 representation guarantees that the algorithm remains efficient, with both time and space complexities tightly bound at O log_2, n. One common mistake people make when converting to base -2 is misunderstanding how negative bases work. Unlike positive base conversions, where remainders are simply taken as is, negative bases require remainders to always be non-negative. For instance, dividing -7 by -2 gives a remainder of -1. This remainder must be adjusted to a positive value, like 1, while also adjusting the quotient accordingly. Failing to do this leads to incorrect results. Another issue arises with edge cases, such as when n equals 0. Here, the output should be 0, but if this special case is overlooked, it can result in runtime errors or infinite loops. Lastly, recursive solutions can also cause issues if not carefully implemented. Without a proper base case or if the input isn't updated correctly, recursion may continue indefinitely, leading to a stack overflow. These are critical areas to watch out for when solving this problem. Efficiency is another common challenge, especially with large inputs. For example, directly concatenating strings for remainders during the conversion process can severely impact performance. In languages like Python, string concatenation can have a time complexity of O(n²), in some cases, making it much slower than appending to a list and reversing the result at the end, which is O(n). Another area where errors often occur is misinterpreting the problem's requirements. Some assume the input number will always be positive, but the problem explicitly allows for negative numbers. This means your logic must handle negative inputs correctly by leveraging the unique properties of the negative base system. Ignoring these nuances can lead to incorrect solutions, so it's important to fully understand the problem constraints. When preparing for interviews, it's important to understand the underlying concepts of negative bases. For example, in base -2, the quotient and remainder must meet specific criteria. Remainders must always be non-negative, which may require adjustments to both the remainder and quotient during calculations. Recognizing the unique patterns of base -2, such as alternating powers like 1, -2, 4, -8, can also help in verifying your solution. If given the choice between iterative and recursive approaches, you should be ready to discuss their trade-offs. Iterative solutions are generally preferred for their space efficiency, as they use O(1) space compared to the O log n space of recursion. Additionally, always make a point to discuss edge cases like n equals 0, n equals 1, or negative inputs early in the interview. This shows thoroughness and helps you identify potential pitfalls in your logic. Demonstrating these insights can leave a strong impression on your interviewer. Understanding related problems can deepen your grasp of the concepts behind base conversions. For example, LeetCode 168, Excel sheet column title, involves converting numbers into a different base system, which is conceptually similar to base -2 conversion. LeetCode 171, Excel sheet column number, reverses this process by converting from a base representation back to decimal. Another relevant problem is LeetCode 405, convert a number to hexadecimal, which focuses on another type of base conversion. And, of course, LeetCode 1017, convert to base -2, is the core problem where these skills are directly applied. Exploring these related problems helps you recognize patterns and strengthen your understanding of base conversion techniques across different contexts. There are several approaches to solving the base -2 conversion problem, each with its own trade-offs. The iterative approach involves repeatedly dividing the number by -2, adjusting the remainder as needed, and building the result step by step. This method is memory efficient, using only O(1) space, but it requires careful attention to correctly handle remainders and the corresponding quotient adjustments. The recursive approach simplifies the logic by naturally breaking down the problem into smaller subproblems, making it easier to manage the sequence of operations. However, it uses O log n space because of the recursion stack, which can be a drawback for very large inputs. A third option is to derive a direct mathematical formula to determine the positions of bits in the base -2 representation. While this can be highly efficient, it's rarely practical due to the complexity of implementation. Each approach has its strengths and weaknesses, so the best choice depends on the specific requirements and constraints of the problem. Great job! We've successfully tackled problem number 1017, convert to base -2. We discussed the basics of negative base numeral systems and practiced implementing a conversion algorithm. Remember to review and practice similar problems to solidify your understanding. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!